this video we are going to talk about the coding of principal component analysis, the mathematics and the theory portion we understood in the last video, and in this video we will talk about we will also talk about manifold learning, understand what it is using the Swiss roll shaped data. We will see what exactly it means. So let us just start. So by the end of this video we will be writing code for uh, principal component analysis and understood manifold learning with Swiss roll data. So from sklearn.decomposition, you know sklearn is the famous machine learning scikit-learn library. Dot decomposition, it is a particular module. Import PCA. Otherwise you can also do from sklearn import decomposition. Then while writing the object you can write decomposition dot PCA and components equals to 2. You can also do it that way, or directly from sklearn.decomposition import PCA. So how you will remember all this? So don't need to remember actually. When you will type in VS Code from sklearn dot, you will keep the word dot. You will get a list of options from which you can select decomposition, because you need to decompose your data. Basically, import, when you will write import, automatically a list of options will come, and the first element will be PCA. Right, decomposition, the most famous algorithm is PCA. So you can write that, and as Python is an object oriented language, so you need to set an object PCA, and n components is 2, means what is the components to which our dataset will be reduced. Suppose our dataset is a 3D dataset, then it will be reduced to 2D. Our dataset is 4D dataset, it will be reduced to 2D. So n components is to what our dataset will be reduced. It is so simple, right? You don't even need to remember this n components. When you will write n and then about to write this, there will be a list of options which you can press. Just simply press enter, and n components in your editor will be automatically written. So x2d is equals to PCA dot fit transform x. So you need to fit our model into our the 3D dataset, right? A 2D dataset reference. So on inverse transformation, the reconstructor is not exactly identical with the initial. So what we are doing, basically we have converted our 2D dataset to 3D to 2D in this way. So we are done in the within first 3 lines only, we are done converting. So it's that simple as that, as simple as that. So what if we again want our 3D dataset back? So when we are going to do it, we'll be doing it PCA dot inverse transform x2d. If we do it, there will be some reconstruction error. Why reconstruction error? Because the exact thing you will not get back again. Some amount of error you will get. What is that error? You can calculate. NP dot mean squared error. So this is also MSE, you can calculate. I have told you what is MSE earlier. Mean squared error it is. So it is the sum of the squares and then we find the mean. And these are NumPy operations. I have explained you in detail in our Python tutorials video, which the link in the description, you can find it. Right. So x is equal to 1. Why x is equal to 1? Because our data is along the y axis. X is equal to 1 means y axis, and x is equal to 0 means x axis, basically the rows, and x is equal to 1 means the columns. So the following will show first two principal components, PCA dot n components, right? So if our data set is 4, it will first show the first two components only. Now in this case our data set was 3, it will show the first two components only. So what is manifold learning? Intuitively, a manifold is a generation of the curves and surfaces or two arbitrary dimension, right? It is another way for reducing dimension, you can say it. We'll see few examples in which data is arranged in a visual manner. So you can see, like in, suppose data is along these lines. Data is along these lines of the manifold. It can be present in this way, or data is along this curve. Data can be present in such a way that it is along this curve. If you are thinking how it is possible, it is definitely possible in many of the cases which you will see. So reducing dimensions in Swiss roll. So let us say in 3D space our dimensions are in this way, x1 and x2. So our data points are this, arranged in a Swiss roll manner, and the frequency is changing with respect to color, right? And basically the type of data is changing with respect to the color. So we are gonna draw separate boundaries. How can we draw that? We want our different data to be different. So I have to separate the boundaries. So if we squash the squeeze roll from above, so squeeze roll squash flashed by projecting on a plane. So what will, everything will be mixed up, right? The black portion will be here, and the red portion will be on this side, and this will be on the yellow on the right side, right? But if we unroll this Swiss, we get particular boundaries. We get our particular boundaries. So which approach do you think is a better idea? So the approach which lead us to particular boundaries, and hence we can segregate our data and understand how many dimension it is taking for our analysis. We should approach that only. So you can see in this way, by rolling out earlier how many dimension it was, 3D. Now it has been projected to 2D, and further also we can get our exact data, right? We have not lost the data, like in the left figure, this figure we have lost the data, you see. But here we have retained the data as well as converted the 3D into the 2D. So reducing dimensions in Swiss roll. But again, what do you think, that always squashing a Swiss roll is a bad idea and opening is good idea, right? You will tend to think from the last slide in this way, but this is not always true. If you open this, you see there is a portion of this green portion, and here is also green portion. So if you open this, you will find the you have two separate boundaries, and using single line or single separations, you cannot really separate those. But you can, you still, you haven't lost the data, right? Have you lost the data? No, you haven't. You can still separate is using straight line, not once, but maybe one, two, three, four straight lines you need to draw to separate this. So here both options are a better idea. First you can unfold it, and even if you squash the Swiss roll, you imagine you are seeing from the above. If you squash, what will you see? If you squash, what will you see? That both options are better, right? So if you go to the previous slide, if you squash the Swiss roll, what will you see? That you, even with a single line you can separate the data. So here's both squashing and unrolling is good idea. And if you compare which one is a more good, so here squashing is more good, because by a single line you can separate the types of data, right? So here both are good ideas, but squashing is more good. So reducing dimensions in Swiss law. So actually in the previous example, squashing was slightly better option. Now if you notice this Swiss roll, do you find something really special about it? Think about it, that what is so special about this Swiss roll? If you squash this Swiss roll, you can still separate the data points by a single line. You can imagine squashing the squeeze roll and seeing it from the top view. You will see a rectangle where the left portion is green and right portion is yellow, right? So with a single line you can separate the data. But if you unroll it again with a single line, you can separate the data. So here we cannot say which is good and which is bad. Both are equally good. So this is a special kind of squeeze roll. So yeah, that's all from this video. Next video will continue learning our algorithms. Thanks a lot.